Hello everyone, welcome back. Now let's begin section 5, properties of norm. Basically we want to study these three properties, but let's begin with the definition of the norm first. Here it is. Let me copy and paste this. And this is the definition of the scalar product. How do you define the norm? Take the scalar product of itself and then square root. From the definition of the scalar product, x's and y's are all the same, so we have, instead of x1, y1, we have x1 times another x1, which is x1 squared. Likewise, x2 squared, and so on and so forth, and then add them all up, and then take the square root. That's how we get the norm. It's a big Pythagorean. Okay, we can use this to prove absolute homogeneity. I'll leave the detail to the students. It's not too difficult. Here, instead of x, start with cx right here in place of just x, and then algebraically manipulate. You can factor c out, c squared out, and then eventually outside of the square root, we get c squared becomes absolute value of c. The detail is left to the students. The last one, that's just too trivial. It's not really worthy of anybody's time, as a matter of fact. That's defined as positive square roots, so always greater than or equal to 0. And then when do we have 0? Inside of a square root is 0. And of course, that's when we have 0 vectors, because we don't have any cancellation there. They're all squares, so they all have to be 0. Good luck writing it down in appropriate languages. Otherwise, rather trivial. Now this one on the other hand, that requires some thinking. Let's talk about it. Okay, it's going to be a little bit difficult to prove this directly, starting from the left-hand side, or the right-hand side, or anywhere. Why? Because norms already include big square root, and it is rather difficult to work with square roots algebraically. So what do you do? Let's make appropriate adjustment. Oh, excuse me, wrong cell. Let us set up on equivalent. Let us set up an equivalent inequality as follows. Instead of this one, let's prove this. Okay, let's begin with the left-hand side. Okay, and then how do we get norm squared? Definition of the norm, if I square here, and that'll kill off this square root here. So basically we are going to get the scalar product of inside. Alright, and then let's work out through FOIL method. First, this one times that one. So x dot product of the x, okay, and then outside x dot product of y, and then inside y dot product of x, but because of the symmetry, we are going to get twice of this. And then finally, last. Or you can use complete square formula if you want to. Basically, this is a plus b squared, so you can use a squared plus 2ab plus b squared. Either way, it'll work out. Okay, let's make a bit further adjustment here. What is this quantity? X, scalar product of itself. X scalar product itself, square root is the norm. So that whole thing is norm squared. The same thing goes over here. This is norm squared. Instead of x, I need y. Okay, all right. So far, so good. Now, let's work on the scalar product part. Come on, I'm having really hard time getting appropriate highlighting. Okay, got it? Okay. So let's pay particular attention to the part that I highlighted in blue. X dot y, and that part can be rewritten like this. And this one is actually a vector. And then that too is a vector. As a matter of fact, why did I do this? I could have done it over here. Okay, and I don't need this line now. Okay, FOIL it out, we get that. And then x dot x, that's norm of x squared. Y dot y, that's norm of y squared. Now this dot product, x dot y, that's the same as norm of x times norm of y, magnitude times cosine of theta. Do you guys remember all this? In module 1, we talked about the dot product in this form. There's a bit of a problem though. In module 1, we did vectors in 2-dimension, and in planar geometry, we could use law of cosines and so on. So this one works out fine. In higher dimension, it's a bit problematic. Is it possible to get an angle appropriately when x and y are given? Yes, it is, because any two vectors determine a plane and then you can get appropriate measurement. That's true, but that's rather cumbersome and it doesn't always work either. If you have infinite dimension, for instance, then everything breaks down. So this proof is, as a matter of fact, a bit problematic because of this cosine of theta. Nonetheless, let's go ahead. So this cosine theta is always less than or equal to 1. So if I drop this cosine of theta or replace it into times 1, let me just drop it. Then we have a quantity that is greater than or equal. You see, this is less than or equal to 1. This one, replace cosine by 1. So this one is bigger. Fourth line is always greater than or equal to the second line. So the third line, excuse me. That's how you get this inequality here. Up to here, here and there, all equality. Now that's inequality because I just dropped cosine of theta. Alright, and then let's work out the right hand side here. A squared plus 2ab plus b squared form. So this is a complete square. So it's nothing more than, well, as a matter of fact, it's just this. Taking the square root of both sides, we are going to get the desired inequality, this one. So here goes the proof, but there's a bit of a problem. That problem is, as a matter of fact, highlighted in red. You see, when you have this dot product, x dot y, can we always write it as magnitude times cosine of theta? In planar geometry, yes, we could do that because we had law of cosines. But in higher dimension, or even worse, in infinite dimension, can we still do that? In infinite dimension, no, it's impossible. You can't do that. But this subadditivity still works, as a matter of fact. How do we handle that? That's something we are going to have to consider in the next section, the optional section. It's called Cauchy-Schwarz inequality, and that's rather formidable. But at this moment, we're going to call this one as, alright, incomplete maybe, but appropriate proof within the scope of our learning. After all, we're going to confine ourselves only to finite dimensional, n-dimensional real space. And even though we proved only for two-dimensional case, it is possible to extend it over to the n-dimensional case. If you have two vectors, then a starting point of the vector and then tip of those vectors form a triangle, and then and there's only one plane that goes to a triangle, kind of tilted plane, and the n-dimensional geometry can be reduced down to two-dimensional geometry. So this method, as a matter of fact, works out. Yes, it is possible to define the angle. It's a bit of a cheating, but for our scope, it's going to be okay. Let's recap this. We want to prove this, but it's a little bit difficult to prove it. So we set up appropriately by taking the square of both sides. Starting from the right-hand side, starting from the left-hand side, we use the property or the definition of the norm. Dot product of itself. Just fold it out, just algebraic manipulation. And then dot product of itself is norm squared, no problem there. Dot product of itself is norm squared, no problem there. Now this inner product is the same as norm cosine of theta. There's a little bit of a logical gap, but within our level, it's okay, so let's just take that. And then cosine of theta is always less than or equal to 1, so drop it. We have inequality, and that resulting right-hand side is a complete square. Norm of x plus norm of y squared. So we ended up this, and taking square root of both sides, we get the desired inequality. Okay, what did I do to this proof 2, hard proof? Do we have time for that? Yes, okay, we do have some time, so let's see. Oh no, not really. Nothing really spectacular. This dot product is less than or equal to this norm times norm, and it's essentially the same thing as inserting this one so that this one is less than or equal to that one because of this cosine of theta factor. And I skipped that cosine of theta factor, but that's it. So no, I don't have to regard it as a hard proof. Okay, all right. All right, all right. Let's say we are done with section 5. As for completing the proof of this subadditivity, let's do that in a separate video when we deal with section 6 as an optional video.